Welcome to this lesson on aldehydes and ketones. In this presentation, we'll learn how to identify these compounds, understand their properties, and explore their important reactions required for the A-level chemistry specification. Position of aldehydes and ketones in organic chemistry, the carbonyl functional group and bond polarity. Aldehydes and ketones contain the carbonyl functional group, C=O, which strongly influences their chemical behavior and physical properties. Understanding aldehydes and ketones is essential because they act as key intermediates between alcohols, carboxylic acids, and more complex molecules used in pharmaceuticals, polymers, and biological systems. Aldehydes and ketones have the carbonyl group, C=O, which consists of a carbon atom double bonded to an oxygen atom which is highly polar due to the large electronegativity difference between carbon and oxygen. Oxygen attracts the shared pair of electrons more strongly, giving it a partial negative charge, while the carbon becomes partially positive, plus. General formulae and structural differences, epoch naming rules for aldehydes and ketones. Aldehydes and ketones share the same general formula, CnH2No, which reflects the presence of a carbonyl group and the absence of additional functional groups. Despite having the same general formula, structural isomerism is common, particularly between aldehydes and ketones with the same molecular formula, such as propanol and propanone. In aldehydes, the carbonyl carbon is always at the end of the carbon chain and bonded to at least one hydrogen atom, giving the functional group CHO. In ketones, the carbonyl carbon is bonded to two carbon atoms and is located within the carbon chain, forming the CO group. This difference has major consequences for chemical reactivity, especially oxidation. Aldehydes are readily oxidized because the carbonyl carbon has a hydrogen attached, whereas ketones lack this hydrogen and are therefore resistant to oxidation under normal laboratory conditions. Aldehydes are named by replacing the final E of the corresponding alkane with the suffix -ol. For example, ethanol becomes ethanol after oxidation. Because the carbonyl carbon in an aldehyde is always at the end of the chain, numbering is not required to indicate its position. Ketones, however, use the suffix 1, and the position of the carbonyl group must be indicated with a number if there is more than one possible position, such as button 2,1. Oxidation of primary alcohols to aldehydes, oxidation of secondary alcohols to ketones. Aldehydes are commonly prepared in the laboratory by the controlled oxidation of primary alcohols using acidified potassium dichromate, 6K2Cr2O7H2SO4. The key to forming an aldehyde rather than a carboxylic acid is careful control of reaction conditions. The alcohol is gently heated, and the aldehyde is distilled off as it forms. This prevents further oxidation to the corresponding carboxylic acid. The color change of the oxidizing agent, from orange dichromate, 6 ions to green chromium, 3 ions, provides visual evidence that oxidation has occurred. Ketones are prepared by oxidizing secondary alcohols, again commonly using acidified potassium dichromate, 6, under reflux conditions. Unlike aldehydes, ketones are not further oxidized under these conditions, so refluxing does not risk forming another product due to the absence of a hydrogen atom attached to the carbonyl carbon. In practical terms, the same orange to green color change is observed, indicating reduction of dichromate, 6 ions. A typical example is the oxidation of propan-2-ol to propanone. Nucleophilic addition reactions of the carbonyl group, Tollens reagent, and oxidation tests. In nucleophilic addition, the partially positive carbonyl carbon attracts nucleophiles, such as Cn or H, which donate a lone pair of electrons to form a new bond. During the reaction, the C=O double bond temporarily breaks, and the electrons move onto the oxygen atom, forming an alkoxide intermediate. Aldehydes are generally more reactive than ketones towards nucleophilic addition because they have less steric hindrance and a greater partial positive charge on the carbonyl carbon. Tollens reagent is an important qualitative test used to distinguish aldehydes from ketones. When an aldehyde is warmed with Tollens reagent, it is oxidized to a carboxylate ion, while the silver ions in the reagent are reduced to metallic silver. This forms the characteristic silver mirror on the inside of the test tube. Ketones do not react, producing no visible change. Infrared and NMR spectroscopy of aldehydes and ketones, A-level exam tips, common mistakes, and summary. Infrared, IR, and nuclear magnetic resonance, NMR, spectroscopy are used to identifying aldehydes and ketones. In IR spectroscopy, both aldehydes and ketones show a strong, sharp absorption due to the C=O stretching vibration in the range 1680 to 1750 cm to the power of 1. Aldehydes also display a weak absorption around 2700 to 2900 cm to the power of 1 due to the CH stretch of the aldehyde hydrogen, which can help distinguish them from ketones. In proton NMR spectroscopy, aldehydes are distinctive because the hydrogen attached to the carbonyl carbon resonates at a very high chemical shift, typically between 9 and 10 ppm. Ketones lack this signal, making NMR particularly useful for differentiation. In A-level exams, carefully identify whether a compound is an aldehyde or ketone before predicting its reactions. Learn the oxidation tests, reagent names, observations, and products. To conclude, aldehydes and ketones are important carbonyl compounds with distinct structures and reactions. Understanding oxidation, reduction, and the characteristic tests will help you answer both multiple choice and longer exam questions with confidence. Thank you for watching.